Thank you. So I want to start with, I said at least one thing that was wrong yesterday. I can only claim a lower bound. I made this claim, but I forgot the hypothesis that you should also assume that pi 0 of f is surjective, which means I is also connective. So in particular, when Ofer asked about this example of, say, A going to A bracket F inverse, whether the fiber, which sits in degree -1, is H unidal, I said, yes, it is, by the result, but I was wrong because the surjectivity is not satisfied there. So this, if you want to understand whether this kind of proposition holds in general, then Ofer's example is the one you should look at.
So it does it all in this example?
I don't know. Yeah. So that would be the example to look at, yeah. Okay, so we're going to continue. We're going to pick up where we left off from looking at dualizable categories from an internal perspective. So recall, so for C in PRL stable, so we have the definition. So I'll rephrase the definition of a compact object in a very slightly non-standard way. So whenever you have a filtered colimit, then for all maps x to some zi, there exists a j bigger than I such that x goes to zi goes to zj is null homotopic. But then the reason for rephrasing it this way is it gives a convenient definition of the notion of a compact map. So whenever the same situation, so this situation here, then for all maps from y to some zi, there exists a j bigger than I such that x goes to y, goes to zi, goes to zj is null homotopic. And we saw that in the compactly generated case, this is equivalent to saying that f factors through a compact object. But in general, there can be lots of compact maps without there being lots of compact objects. And we had this proposition that said C is dualizable if and only if it has enough compact maps, but not necessarily enough compact objects. And one way to phrase this was saying that C is generated under colimits by objects of the form sequential colimit x0, x1, x2, where all these transition maps are compact. And let me recall also that the notion of morphism between dualizable categories that we were interested in was that of strongly continuous functor. So a functor that commutes with colimits and whose right adjoint commutes with colimits. And now there's a nice way of understanding this condition in terms of compact maps. So let's say C is dualizable, D arbitrary in PRL, and then F from C to D in PRL, so meaning it preserves colimits, then F is strongly continuous if and only if F sends compact maps to compact maps. So it's just like how functor between compactly generated categories is strongly continuous if and only if it sends compact objects to compact objects. It's the same story, you just use compact maps instead.
So generated under colimits. This means that every object is obtained as a colimit or by iteration. That is, you have to enlarge the class each time by taking more and more colimits.
It's enough to do it just once, and in fact, so if you take it if you say express this in the weakest possible sense, then you get a strong conclusion that C is obtained by freely adjoining Aleph-1 filtered colimits to these basic guys. And where by basic I mean one that's of that form.
So here you need stability, right?
Yes. Yeah. Did I? Oh, well. Okay. Sorry.
Okay, but I just want to check whether if you don't have stability, then I mean most of statement just do true by small modification or.
Yeah, probably there's a way to phrase the definition of compact maps so it makes sense in the non-stable context, but this way of phrasing it definitely is not the right one in the non-stable context. There's different variants of this definition.
So, are objects of this form exactly the Aleph-1 like compact?
Yes. Yeah, these are the collection of these is closed under countable colimits. That's maybe not obvious, but it's a good exercise, and that implies together with this, that implies that they are exactly the Aleph-1 compact objects. And maybe I'll say that these are. Okay, where's my eraser?
Right outside. Oh yeah, I found it.
Oh, thank you. It's on the eraser cleaner. Yeah. Okay. Okay. Now I don't even want it. Okay. So now I'm going to use this perspective to describe how you can just build dualizable categories for free. So building dualizable categories. So suppose C is just presentable, and let's take S to be a collection of maps. In C, such that, and I'm going to have some axioms which are closure properties for morphisms in S. These axioms are not really necessary for the construction of the dualizable category, but for it to have a nice universal property, then we'll use these axioms. So the first one is that, so if F, G, H are composable, then G in S implies F, G, H in S. So a kind of two-sided ideal. The second condition is that, well, let's say if F, G in S, then let's say the direct sum is in S.
So this means maps remain equivalent pairs of maps. It is maps in the homotopy category.
Yeah, let's. Maybe I'll say maybe I should also add axiom closed under homotopies. Yeah. So, but it's actually. If you read this the right way, it's a consequence of this when you take F and H being the identity and remember that composition, well, anyway, yeah.
Maybe 0 should be in S.
Well, doesn't it follow from this, Ofer?
No, but if you don't have anything in S, you can't do.
We'll see if anything I say is wrong when S is the empty collection. We'll see. I don't think anything will break if S is the empty set. Yeah. Okay. F in S implies, yeah, let's say suspension of F and desuspension of F. Some of these might be, some of these might follow from others. I don't know. So, the fourth one is, I almost want to say that So we'll start with this situation. We have x going to y, and we have x going to x prime, and y going to y prime. And these maps are both in S. A strong axiom would say that the cofiber is also in S. So I'll use a x double prime for the cofiber and y double prime. A strong version of the axiom would say that this is in S, but so these are these vertical things are going to be cofiber sequences. But that strong thing is not necessary, and it's also not satisfied for many choices of S you want to take. So I'll ask only the following weaker thing, that if you compose two things, two commutative squares, you pile them together where all of the horizontal maps are in S, and you again make a cofiber sequence, then this composition here is in S. So that's the conclusion. Require this.
Identities, you haven't said anything about identity.
Identity should not be required to be in S.
So when you write the commutative diagram, of course it's commutative up to homotopy. That is the functor in some higher sense from the category to the...
Yeah. What I've drawn here is a functor from delta 2 cross delta 2 to my infinity category. Yeah. Okay. So, well, example would be for C arbitrary, S equals the collection of all compact maps. So
here xy by z is just any maps in S.
well,
or it's also equal.
These are the only hypothesis is that the horizontal maps here are in S.
Okay.
Yeah, I mean all of them individually. Yeah. Okay, and there. Well, we'll do more examples in a sec. But what's the proposition? So there exists a dualizable infinity category. Let me call it a C comma S dual. With the following universal property. Well, with a colimit preserving functor to C such that for all dualizable D, the infinity category of strongly continuous functors to this CS dual is equivalent to the infinity category of all functors in PRL, so just colimit preserving, such that compact maps go to elements of S. So in particular, if you apply this in this example, you find a way of converting anything into a dualizable category. But choosing smaller collections of S or larger or different collections of S give you additional flexibility in constructing dualizable categories.
Is there a name for these kind of ideals?
I don't know. I just kind of made up the axiomatics.
This is true.
What's that?
If this holds, then you can take the zero map of the zero object, which is compact, its image is in S, and so S is non-empty. So this proposition implies that S is non-empty.
Darn, he's right. Happy? Wait.
Then you get all 0 maps because you can compose on the two sides.
Yeah, okay. I think hopefully it's correct. Yeah. Wait, Ofer. No, I can't. You're right. Okay. Okay, so.
It can also be true that C comma empty is just empty.
C comma empty.
C comma empty dual.
But there's no empty category in PRLST.
Yeah, that's a good point.
Yeah. Okay. So, so the construction. So this CS dual is going to be a full subcategory of ind of C, and it's going to be generated under colimits by basic objects, which are as follows. It's going to be very similar to our previous discussion, but with a twist. So before I had a sequential colimit that's indexed by the natural numbers. Now it's going to be a colimit indexed by the positive rational numbers. That's a poset under less than. And now it's hard for me to write all the, the things, but so all transition maps are required to lie in S. So each one of these is in particular a sequential colimit sequential colimit with transition maps in S. But moreover, each transition map can be factored through another such guy. And it's that extra stuff, which comes from the colimit indexed by the rational thing, that lets you check that this thing is dualizable. And then the axioms actually imply. So for that check that is dualizable, you don't need the axioms, but the axioms imply that these basic objects are closed under countable colimits and are the Aleph1 compact objects. So checking closed under accountable direct sums, there's some trick with writing a countable direct sum as a colimit of finite direct sums and then passing to some diagonal in system. Yes?
If you take class S equal to all compact maps, but in CS dual, and you apply the construction, is this idempotent? Like, do you get CS dual again? Okay, start with.
Oh, if you start with any dualizable category and you take the class of compact maps, it's the same. And that then you might say, but wait, you said the Aleph1 compact objects were just given by this, where lambda is in natural numbers, not where lambda is in rational numbers. So why aren't we getting less? And now I'll make a remark. So remark, if every f in S is a composite of two elements of S, then you can use natural numbers instead of.
And it is again in the Aleph1 of the Aleph1 compact.
Yeah, well, I already claimed that it's dualizable, and I already told you that every dualizable category is Aleph1 compactly generated, so that follows. Yeah.
And if you take the functions, the maps in S, which admit a system of factorization, that is your coherent way of putting things in the middle each time, then you get a possibly much smaller class.
Yes.
Does it satisfy the axioms, and is it exactly the image of the compact maps for elements in?
Yeah, that's my claim. Yeah.
Okay.
Yeah. Yeah, using these axioms, yeah. Okay.
So I just want a technical question. So how is this Q positive, rational numbers special in all, how do you say?
In all posets?
Yeah, I'll find with categorical.
Yeah, there's a theorem of Cantor. I don't get to say this that often. There's a theorem of Cantor that the poset of rational numbers is characterized by, well, maybe I have to worry about endpoints or something, but basically it's linearly ordered and it's dense, and it's countable.
Yeah, no first and last elements. Between any two there is one. Okay. Countable. Okay.
Yeah, I think. I don't know if I need to say non-empty too, but yeah.
So if we are given a countable poset and it's first pick a lead, total ordering contain this, then it reduces.
Yeah, this is the only example of the kind of phenomenon we want to see. Where it's a sequential colimit, but each map factors through a similar sequential colimit, and so on and so forth. Okay, so I do want to get to analytic geometry. I probably won't get to much, but so I think I'll leave the following as good exercises. So use this to construct the inverse limits and sort of dual and internal Homs in PRST dual. So what you can do is you can take the usual inverse limit in PRL and then choose your S appropriately, verify the axioms, and go. And these are, I wish I had more time to give examples. Well, Thomas already gave a very good example of this, of these constructions really doing something interesting. So in particular, it can happen that you have a sequence of dualizable categories in strongly continuous maps. The inverse limit in PRL is already dualizable. In fact, compactly generated it can be, but it's still not the dualizable inverse limit. So that's very crazy, but it happens, and yeah. So it's a very interesting and non-trivial construction.
Is it true that the maps in S are actually compact in C, S dual?
Well, it's not a well-defined question at the moment, because arbitrary map in C doesn't necessarily. Yeah. Okay. So I want to discuss a very fundamental example of this construction. Something I've been kind of hinting at for a while, and it relates to a notion called rigid categories. So.
By the way, so in the dualizable category, is it what any compact map is a product of two?
Yes. So rigid categories. So this was a notion defined by Gates, Gorey, and Rosenblum. And they gave, in the language I've been using, they gave an external characterization, but I'm going to skip, I'm not even going to mention that, and I'm just going to give the internal characterization. But what kind of things are these? So these are special kinds of objects in C-alg PRL. So presentable symmetric monoidal categories where the tensor product commutes with colimits in each variable. And to motivate the definition, let me make a table of analogies. So we have a compact object, and we have compact morphism. Now those make sense in a general, we'll say presentable category. But when you have a tensor structure, there's something which is in practice often closely related to the notion of compact object, which is dualizable object. And the corresponding notion for maps is what's called trace class map. And I'll give the definition of what's a trace class map now. So now C is in C-alg PRL. So F from X to Y is trace class. If there exists a map from 1 to, I have to be careful to say what I mean by this. So by this, I don't mean X should be dualizable. I just mean the internal Hom from X to the unit object. Such that F is homotopic to, you start with X and then you go to X tensor X dual tensor Y, and then you contract via the evaluation pairing to go to Y. So remark, what's the reason for the name? So if X equals Y, these are exactly, well, the reason for the name is that if X equals Y, then a choice of such, 1 going to X dual tensor Y, gives rise to a notion of trace, which will be an endomorphism of the unit. So there's a bit of an annoying business, which actually doesn't cause problems in practice, that if you fix only just the homotopy class of X, then then there could be several different so-called witnesses to F being trace class. And each one of them potentially gives you a different trace. But okay, this is just we're not actually going to use this notion of trace or anything. So I just wanted to explain why it's called trace class. And another remark, so the identity map from X to X is trace class if and only if X is dualizable, in the strongest possible sense. So that's one justification for this analogy. So rigid categories have magical properties. Oh, I didn't define it. Sorry. C in C-alg PRL is rigid if and only if the collection of trace class maps is the same as the collection of compact maps. So if C is compactly generated, it's the same thing as saying that the...
I mean, Dustin, sorry. I mean, do you want to ask it to be dualizable, and do you want the tensor product to be strongly continuous, or does it follow?
This follows. Yeah. This follows.
And the unit compact?
Yes. Well, unit is dual.
But the other ones I don't. Oh.
Yeah.
Really?
Oh. I'm not saying it's obvious it matches with Gates-Gorey-Rosenblum's definition. Okay. Right, so yeah, if C is compactly generated, it's the same thing as saying the dualizable objects are the same as the compact objects. So this is just the obvious generalization of that kind of familiar condition to the non-compactly generated case.
Does it imply dualizability?
Yes. Yeah, that's a it's a good remark. So or wait a second. No, sorry. Did I mess something up? Just a sec. Sorry. I think I misanswered both of those questions. Yeah, I should.
So it is dualizable plus this, I guess.
Yeah, but I want to say. But I want to make it slightly less obvious, so yeah. Well, no. Yeah. Okay. Yeah. Sorry. Plus dualizable. I'm sorry. Yeah. Sorry. I misanswered both of those questions. I should. But I want to say maybe that this perspective can help you prove dualizability, because the trace class maps will provide good examples of compact maps. And for dualizability, you need enough compact maps. And so if you understand the trace class maps, you often get a good source of compact maps. So I was wrong, but there's some truth in what I was saying. That, yeah, not.
So wait, what's the claim there? If and only if?
If and only if 1, trace class is the same as compact, and 2, C is dualizable. Just as a bare, forgetting the commutative algebra structure. Yeah. Okay. So rigid categories have some remarkable properties. So the first one is, so any map F C to D with C rigid, a map in what category? In C alg PRL with C rigid, and let's say the unit of D compact is automatically strongly continuous. So if you have a symmetric monoidal functor with a rigid source, you don't have to check this property. And the second thing, which is the raison d'etre of rigidity, is that rigid categories are suitable base categories in this theory. So the category, so for C rigid implies that the category of C modules in PRL stable has nice properties. So the first one would be, so if F from M to N in this category is strongly continuous, then the right adjoint is automatically C linear.
You mean it's a data also that there is?
No, it's not a data because there's automatically a comparison map. Yeah. Not a data. And B, so an object, again, M in mod C PRL stable is dualizable in this world here, if and only if M viewed as just an object in PRL stable is dualizable. And it's in particular this direction that's interesting, believe it or not, that if you build a dualizable object in the C-linear world, then its underlying category is automatically dualizable. Why is this interesting? Well, remember we had some sources of dualizable categories coming from, say, idempotent algebras. Now we're allowed to, now we get more because as soon as we take a rigid category, then we only need to have idempotent algebras in that category. And you can build rigid categories where the tensor product is some sort of completed tensor product. And now you don't have to, for idempotent algebras or for getting dualizable categories, you don't need to have algebraic tensor products anymore. You can take completed tensor products once you build the right base category. And this gives you many, many, many more examples than you had before. So this is important because now C can encode completed tensor products. And that gives you more examples of idempotency. And the other nice thing is that 3, so the functor C tensor C, which is the tensor structure, is strongly continuous. And that gives a E-infinity ring structure on the K-theory of C, for example, on the continuous K-theory of C. And now let me make a warning. So we had this category a D of K yesterday, which was encoding this Karoubi situation with K-theory of compact operators. This satisfies 3. Oh, and actually I also wanted to say 4, C is canonically self-dual. So you can write down, you can use the extra right adjoints you have to write down a canonical self-duality between C and C. I want to warn you that this satisfies 3 and 4, but is not rigid. So this is one reason why I said yesterday that this is not the optimal category to be considering, or this ideal in bounded operators given by compact operators is not ideal. And the reason is you get a symmetric monodal category, which is good enough for getting an E-infinity ring structure on your K-theory, but it's not good enough for working relative to. It's not a rigid category. Okay. So where are we? Okay. Okay. So now but there's a fix. So proposition, the full subcategory, so rigid inside commutative algebra objects in PRL stable. And now it really is a full subcategory. Remember I said any strongly continuous, any morphism here is actually automatically strongly continuous. So now, yeah. So it's really a full subcategory. The inclusion of the full subcategory admits a right adjoint. So C goes to C rigid. And what is this? It's an instance of this construction. You take C and you take all trace class maps. And then dual.
Dual, like opposite, no, dual in the sense of...
No, this is I have this general construction, C comma S dual, where I take these in systems indexed by rational numbers. This was my notation for that construction.
Okay.
So my class of maps S I'm taking to be the trace class maps in C.
Okay, and in number 4 property, where you say C is canonical self-dual?
Yeah, that's in the sense of, so C is isomorphic to fun LC to spectra. And this is the dual of C in the Lurie tensor product symmetric monoidal structure. Yeah. And by the way, this is, I'm sorry?
You didn't require their stable.
I meant to. Thank you. Yeah. Okay. So now some examples in analytic geometry. Okay. So I'm going to return to this situation that we had yesterday, where R will be a commutative Noetherian ring, complete with respect to an ideal I. And I had this ad hoc description of what I called the nuclear category of R, using these idempotent algebras with some endomorphisms of some completed direct sum modulo compact endomorphisms. And now I want to give a better perspective on the same category. So, well, to R we can associate using this solid formalism. So this D-solid RR, for example, it's a certain large category of condensed R modules. It's basically condensed R modules that are in some sense complete, in some eidetic sense, but not like the usual derived eidetic completeness. So it's but only sort of locally eidically complete in some sense. You can also take direct sums without eidically completing, and you can also invert elements without recompleting, and so on. So it's a bigger world. And then it is, well, modulo set theoretic technicalities. It's in C-alg PRL-ST, and then we take its rigidification. And this is the same thing as what I was called nuc R. And another feature of this rigidification is that it kind of destroys some subtleties. And one of the subtleties it destroys the dependence on the, there's some kind of subtle business about the second coordinate, but it doesn't matter for the purposes of this nuclear category.
So here you put Z?
Yeah. I mean, you can integrally close it in R if you like, but wait. You could also put anything in between. It's always going to be the same. And so more generally, if sort of, so RR to like, let's say A plus is a rational localization of SPA RR, well, we get a category similarly D solid A plus, and then you rigidify, and this is nuke A. Again, it doesn't depend on the second variable. And then the theorem of Andrechev is that so both sort of SPA AA plus goes to nuke A, and SPA AA plus goes to continuous K theory of nuke A, satisfy descent.
Is this for like a V topology or?
No, this is for just the topology, usual topology on rational opens. Yeah. Yeah, not at all for the V topology or anything crazy. Just on this nice spectral space here.
So you have on rational domains, and this is for check or hypercovers or?
I just say check. Yeah. Probably if you don't have a Krull dimension assumption, there's no hope for hyperdescent. Yeah. Yes.
This nuclear is dualized.
Yes, it's dualizable. In fact, it's rigid by construction. Yeah. Mm-hmm. So this sheaf here is taking values in rigid. And I want to sketch the proof because it shows. Well, I started the first lecture saying, giving some motivation about why small stable infinity categories are not enough. And I said in analytic geometry, even though in some cases, also by results of Andrechev, you have descent for perfect complexes, you don't have descent on the level of K theory because for perfect complexes in analytic geometry, you don't have localization sequences. But what happens in this proof, I mean, I hope Greg agrees with me, or I don't know, feel free to chime in at any point if you want to make a comment or anything. But what's happening in this proof is that this situation now all of a sudden looks exactly like the situation in ordinary algebraic geometry. So the first thing you can check is that A, which is some Huber ring of some sort, but strongly tied to R, is actually naturally a module in nuke R. And then even more, A is idempotent in nuke R. And then even more, nuke A is just A modules in nuke R. And then 4 tensor products of A's corresponds to intersection of rational opens. This isn't actually the most convenient way of doing the proof in practice, but this is kind of one way of indicating what's going on. And then 5, well, you need to know that covers are the same. Covers are recovered algebraically. So let me just, a special case. So you have R going to A prime, going to A tensor A, R A prime is a pullback if and only if the corresponding rational opens cover. Or, well, let me, sorry. Let me just, yeah. And then you see that these rational opens in rigid analytic geometry, from the perspective of this nuclear category, they might as well just be like Zariski localizations like you're used to. All the exact same formal properties. A is not given by just inverting an element in R, that's the complication. But once you decide to work in this category instead of usual algebraic modules, it might as well be given by inverting an element of R. It's just idempotent. Tensor product mimics intersection, and this kind of construction mimics covers. It's all exactly the same. And this implies both claims, both this claim and this claim, by the exact same argument as the scheme case.
So, being an idempotent, you have to give an isomorphism A tangent A is A?
Yeah.
But is it uniquely defined by saying that F1 that should present 1, or?
No, it's, I mean, it's just a condition, actually. It's just that the multiplication map, A tensor RA going to A, is an isomorphism.
Ah, okay.
Yeah.
Okay.
Sorry, is nuke R a full subcategory or subcategory of this solid R in this case? Because in general, this construction only gives a functor.
It's a full set. Thank you. I perhaps should have mentioned, thank you very much. But when I was discussing this rigidification, I should make a remark. So if the unit object in C is compact, then C rig is actually a full subcategory of C. Thank you very much. And this is the case for these solid categories, that the unit object, the unit object is compact. And so then it's really just a full subcategory. Okay. So let me give just one example of what's going on here. So if you take U to be a certain open, which is so SPA R the analytic locus. So if R is a formal scheme given by completing along some ideal, and then you kind of puncture at the ideal you completed along, and this is something you can do in the world of adic spaces, then this nuke U is just the quotient of nuke R by the full subcategory of I torsion modules, I power torsion modules. And this is the same in nuke R and the usual dr. So in this nuclear category, in the I-adically complete case, once you look at I torsion modules, you lose the exotic behavior. It just reduces to usual algebraic situation.
So I power torsion, you mean killed by power of I?
I mean that if you, let's say I is generated by a single element, if you invert that element, you get 0. Yeah.
Ah, okay. Yeah. Only in the sense, so because it is all topology. Okay.
Yeah. But it turns out that those torsion modules, they're actually all discrete. So that's the little claim I was making here in this nuclear category. If you have something torsion, then it's automatically discrete. And the conclusion is that K theory of U is the same thing as this continuous K theory of R, modulo the usual K theory of perf R on I. Modulo, which by Sasha's result is the inverse limit over n of K theory of R mod I to the n modulo K theory of perf R on I. Yes. So immediate corollary is a theorem of Kertz Strong, comma. So the most important, as we learned in Shane's talk, the most he didn't say this, I'm saying it, the most important theorem in the K-theory of singular schemes. So if f from x to y is a proper map of Noetherian schemes, let's say it's an isomorphism outside closed subscheme Z, then so we have k of x, k of y. So pull back.
Yeah, it could even with the quotation mark or without the quotation mark.
So the proof I'll present only gives it without the quotation marks, but I claim that you can refine the argument a bit and get the quotation marks too. Did I state it wrong?
No, just the arrows should be.
Oh no, oh no. Ah. Tell me where.
The arrow goes the other way.
Thanks. Like that? Is it good now? Thanks. And then the pullback goes the other way too. Okay. Yeah. Okay. So the proof. So using the hypothesis. So using isomorphism outside Z, we can replace K-theory of X with K-theory of X supported on F inverse of Z, and K-theory of Y. We have to do it both at the same time, but with K-theory of Y supported on Z. That's just the usual localization sequence in algebraic K-theory, because the open complement is the same. And once we make this replacement, then we don't need that hypothesis anymore. We throw it out. And then, but then because it's proper and it's an isomorphism outside an open subset, but then if you look at X completed along F inverse of Z, and you take the adic locus, that mapping to Y completed along Z, take the analytic locus, then this is actually an isomorphism of adic spaces. In particular, it's the same on K-theory.
Sorry, which assumption did you throw away?
Where are we? Hello, Shane.
Which assumption did you throw away? And what do you
after I make this replacement here, I throw away the assumption. Oh no, I don't throw it away. I keep it. Sorry. Yeah, I still need it for this conclusion. Yeah. Sorry, I don't throw it away. Okay, so in particular, it gives an isomorphism on K-theory, and then that gives the proof by the description of the K-theory over here, which globalizes.
What is written before the isomorphism?
You mean before this isomorphism?
Yeah, to the left from this.
Oh, but then.
But then.
Yeah. So, yeah, actually, so I can tell a personal story. So, Georg announced this theorem at a talk in Copenhagen, and I was in the audience, and I immediately, I hadn't even heard of this ever, but when he explained this statement, I immediately had this vision that the true explanation should be that in such a situation, the rigid analytic generic fibers are isomorphic, and the real explanation should be that there's some K-theory invariantly defined on such guys, which is just calculated by that formula here. It's amazing that with all this work of Sasha and Greg and everybody that it actually came true. So I'm very pleased with this.
But this is weaker than their statement.
You had to ruin the moment. You mean because it's not a pro-isomorphism? No, but I'm saying you can actually. I had this Noetherian hypothesis, but it works in some non-Noetherian situations as well. And if you cross with a profinite set, then you get the same statement. And then you deduce this holds in condensed spectra. And then there's a little lemma that if you have a pro system in condensed spectra, then a sequential pro system in condensed spectra, a sequential pro system, then the functor of taking limits in condensed spectra detects isomorphisms. Or detects weak equivalences, sorry, in this truncating sense. So you can deduce the full statement, okay, yeah. But I didn't want to get into too many technicalities. Okay, other questions?
Can you deduce pro-excision this way?
I don't know what pro-excision is.
Like Milnor excision.
Never thought about it, yeah.
But for Milnor squares, we don't have a excision in K theory in general.
Yeah, but you need the process. So, like the difference is instead of a proper morphism, you have an affine morphism.
Yeah.
But you still take this pro system, so caution.
Other questions? Let me say just a couple of things about the Archimedean case. I want to phrase a conjecture, because last time I phrased a conjecture in a talk like this, Sasha proved it. That was this continuous K theory of R iadically completed. So I'm hoping it'll happen again. So I want to make sure I state the conjecture. So I want to talk about the Archimedean case. There I took some solid theory and I applied this rigidification and I got a nice rigid category, in particular dualizable. Well, we also have this d liquid P over the complex numbers, and we can also take the rigidification of that. And again, it's something we actually saw before, very briefly. So it's the same as you take, say, bounded operators on a Hilbert space, and then the idempotent map from this to bounded operators modulo this Schatten ideal S0 plus. Another way of saying it is compact operators whose singular values form a rapidly decaying sequence. So that's a certain kind of Archimedean functional analysis. And again, it's independent of P. There's a parameter P involved in this theory, but it disappears when you rigidify, just like with the R plus variable not mattering. And it's also the same as if you decided, okay, I put a symmetric monoidal structure on this, and I put a symmetric monoidal structure on this, and I said those were not rigid, but if you rigidify them, you always get the exact same thing. So there's other variants you could put in here, and all their rigidifications are the same. So this is truly a canonical object. It's basically the only thing in Archimedean only category you can write down in Archimedean functional analysis, base category, which is rigid. So it's definitely the right thing to work over. And the crucial question is, what is its K theory? So, big question. This deserves a name. Let me call this category, I'll call it, it's some analytic version of the derived category of complex vector spaces. So what is, so now let me produce an interesting class in this K theory. So construction, which in different language goes back to Karoubi. Maybe he didn't quite remark it lives here, but okay. So there exists a canonical, and it's supposed to be an inverse bot class, but the bot class doesn't exist. So I'll call it the Karubi class instead. I'll denote it kappa. So it's morally inverse bot. But since bot only exists when you pass to some homotopy invariant theory, and this one's not going to be homotopy invariant, it's funny, you see in this world it's actually the inverse to the bot element that's more fundamental than the bot element itself. So proof, I guess. But now we can give a very interesting proof. So so we can look at the category of sheaves on the topological space S2, but I'll write that as P1 over the complex numbers with coefficients in D and C. And then we can map that to the quasi-coherent category, quasi-coherent analytic category for P1. For the analytic space P1, which is one possible definition of this, is simply you look at modules over the sheaf of holomorphic functions inside this category, sheaves on P1C with coefficients in D and C. So inside this category you have a ring object given by the usual sheaf of holomorphic functions. Those holomorphic functions are basic examples of functional analytic objects that actually naturally live in here. And you get this symmetric monoidal functor like this. So it's a tensor functor between rigid categories. I forgot to mention sheaves on a compact Hausdorff space is also rigid, not just dualizable. Now you apply K-theory. And you get a map by Sasha's theorem calculating the K-theory of sheaves on a compact Hausdorff space. The right-hand side, maybe I want to do relative to, I want to do it relative to infinity. So let's work relative to. So I make this category for P1 and I make the category for the point, and I'm going to do some cofiber. So then you get a map from loops 2 of K-theory of D and C to K-theory of this Dn quasi-co P1. But then you can just take R gamma, which is a functor back down to Dn of a point, and that maps then to K-theory of D and C. In fact, there's actually this is the same thing as the Bailenson semi-orthogonal decomposition works in this case as well. This is just 2 copies of K-theory of D and C, and we're kind of, in the relative thing, we're just killing one of the copies, and this is actually an isomorphism. And then magically, we've produced a map like this of K-theory of C modules, and that's exactly picking out a class kappa in degree -2.
What do you mean by mod or sheaf?
Oh, so inside this category, there's a sheaf of rings, which assigns to an open subset the ring of holomorphic functions on that open subset, which can naturally be viewed as an object here.
D and C is
It's this full subcategory of whatever, this functional analytic nonsense. So, okay, well, this one is simplest, because this sits inside a derived category of condensed C vector spaces. So I've given you a topological vector space, so it gives you a condensed vector space, and I claim it lies actually in this full subcategory here. So it's the usual topology on rings of holomorphic functions. Yeah. Have I gone over time? Or no, I have 5 minutes. Yeah. Okay, good. Yeah.
So how do you get
this isomorphism between K3 and K1?
Oh, it's a version of Gaga. We basically proved it in these notes, yeah, on complex geometry. So
there is an equivalence of.
Yeah, it comes from an equivalence of categories, just like in the usual. Yeah, yeah. Okay, so you get this class in degree -2, and then so
maybe there's something very easy. I mean, what's the first function? I mean, you somehow tensor with this whole homomorphism.
Yes.
But why is it still quasi-coherent?
That's magic, and I didn't realize it until very recently. But
I mean, in tell sheet, I mean, a tensor with O is not necessary.
I know. There's something magical going on here. I'm glad you pointed it out. I don't have time to explain it, but it's very interesting. Yeah. So I claim if you make this definition on like a compact Stein instead, then it's actually affine. So this category is the same thing as modules over that affinoid ring in this base category. Weird, but true. So you kind of get automatic quasi-coherence in this setting. Very strange, but yeah. Okay, so
what is written under relative something? Under the. This is from the previous blackboard.
So there's a theorem, I guess. So if X is a smooth and proper complex analytic space, then this. Let me write K and X for you do this thing. You do this thing, and then you take a Efimov K theory. So if you invert the Karoubi element, then you get the usual topological K theory of the complex points. That's the first thing. And then the second claim is that if you take TC minus of this, so dn quasi-co x relative to the category over a point.
So but this is just HC minus.
Yeah, that's right. That's the same as HC minus. Thank you. Yeah, we're in characteristic 0. It's a good point. Maybe I should say HC minus. So this has a motivic filtration by these filtered pieces of the Hodge filtration on de Rham cohomology. That's the most elementary part of the theorem, or well, 2 and 3, I guess. And then. So then 3 is that if you take HC minus of x, HC minus, you invert Karoubi, it's the same thing as HP of x, which is filtered by de Rham cohomology. And then the conjecture, and that, well, the result of this is that if you form this construction, so Kn x kappa inverse cross over HC minus x kappa inverse HC minus x, this is filtered by de Lean cohomology. And then the conjecture is that this analytic K theory of X, then 5 is that there exists a natural map from Kn X to this fiber product. Well, actually, it's almost obvious from what I said, to this thing that de Lean cohomology is filtering. And then the conjecture is that that map is an isomorphism.
What do you mean by filtration?
I mean, there's a filtration on it where the associated graded pieces are Deligne cohomology. So what's the difference between this guy and the Karoubi thing, K-theory of compact operators? The difference is what in operator algebra people call higher invariance. Non-homotopy invariant things like actual numbers that you're picking up in this in the Deligne cohomology part or the cyclic homology part. So actually, if you took Hochschild homology of this Karoubi category, it would vanish. I mean, this compact operator category would vanish, but the Hochschild homology of this is very much non-trivial. And the claim is the conjecture is that, this is the conjecture. So I think I'll stop here. Thank you very much for your attention.
Thank you very much. Questions?
Yes.
Have you looked at like degree 0 or something? That isn't possible?
It's not, in this generality, it's not easy. Let me say that...
C itself. No.
Yeah, for C, let me say that if you give me an R, if you prove this when x equals point, then, if you prove this when x equals a point, I think you probably will not have a hard time extending it to general x. So I think all the essential difficulty is in the case where x is a point. And all I know about that case is that this comparison map here is an isomorphism in non-positive degrees. I believe I could get K1 if I really sat down and worked hard. But if you ask me about K2, I have no idea. And I really hope people will help me with this. Some people out there.
You define trace class categorically, so can you relate it to the classical notion of trace class on the set of equilibrium space?
Yes. Yeah, so I'm pretty sure it's true. I think I checked it, that if you take this category here, this DBH category, then the notion of trace class there is exactly the same. Well, sorry, I mean, so you take two honest, I mean, this is a derived category of some sort, but you can take two honest Hilbert spaces and ask what's a trace class map. And I believe I checked it's exactly the same thing as a usual trace class map, but the proof was kind of interesting because what came out when you unravel the definitions was not literally a trace class map, but believe it or not, a composite of two Hilbert-Schmidt maps. But then it's a result that's exactly the same as the trace class map. So you have to, this internal Hom in these, it's in an int category, so you actually have to think, about what it's really doing.
So you say that this essentially is the case of a point, then generally, I wonder if you solve this for points, then does that also follow that if you replace this x by some DG category over C?
No, I don't know anything about that. Yeah.
I know. Still talk about the last conjecture.
No, you'd have to a priori know some kind of Kunith property for this theory, which I mean, I would have no idea how to attack that. I said it in the abstract, but just I should of course mention my collaborator Peter Scholze. And I should also mention that one of Peter's students, Koaoki, I believe he's using some perspective, I don't know if it's exactly this perspective or a similar one to prove new Riemann-Roch theorems in the setting of complex analytic geometry.
Wait, so the statement is this K of D analytic of X? Or?
Oh, this here? Yeah. You're asking what the definition of it is? Yeah, so it's K theory of, I mean, I explained this for P1, but you put an X here, and it's K theory of this category. This category. Yeah. Yes?
Sorry, maybe you explained it, but maybe I missed it. Do you know if there is some kind of motivic filtration on this analytic K theory?
Well, only if the conjecture is true do I know it.
But you don't have a concept?
I don't have an a priori. No. Okay. No. I mean, it would be nice. I mean, at least it would be nice, at least when you rationalize, to know that you can do something like use Adams operations and so on. But I don't even know that. So Adams operation. So Akil Matthew and Thomas Nikolaus, I think, or maybe they've investigated the polynomial functoriality of Efimov K-theory. So that could possibly be a first step to constructing such a filtration, at least after rationalization. But yes.
I just had a question. So this pullback, I guess, is a lot like the Selmer K-theory, construction of Selmer K-theory.
Yeah.
I was just wondering, like, in the setting of Selmer K-theory, you have this picture with the P-completion, the generic fiber, and the rigid generic fiber. I was wondering if there's any analog of these terms in the pullback.
There are many analogies to mention. Another, I mean, that wouldn't be the first one that popped into my mind. But let me try to. Well, there's a big difference, which is that kappa lives in degree -2. I guess you could say there's some sort of analogy there, because I was saying that. That inverting this makes it topological. You're destroying the coherent information, and that's also what's happening when you pass from symptomic cohomology to Étale cohomology of the rigid generic fiber. So I think it's a nice analogy, but I don't know. Yeah, maybe this is the analog of that.
But, I guess one difference is that in Selmer setting, we'd be getting Selmer K-theory and not the K-theory itself. Yeah,
that is a big difference. That's one of the reasons I find this conjecture so interesting. But here's why I'm confident. You can prove a priori that this satisfies a descent, or actually, it turns out it satisfies co-descent. So it turns out if you remove this word, then the correct version of these results uses compactly supported everything instead. It's just like with Efimov's calculation of K-theory for locally compact Hausdorff spaces. But anyway, you have co-descent for the analytic topology. So I can't imagine that, So I find it very hard to imagine that this fails, because both sides have the exact same functorial properties, the same formal properties, and
Any more questions?
If not, let's thank Dustin again for